A little bit about who we are. Next to me here we have Adam, Mr. Mechanic.
Hi, Mr. Mechanic to you.
Thank you very much, sir. And myself. You will find both of us have been spending years trying to get SQL Server out of its performance troubles, and we'll share some of our secrets today with about how we do that.
Excellent. So, our goal, effectively, is to have you use your brain. That's good, right? You seem scared. But it's there in your head. It's ready.
Yes.
It wants to be used, trust me.
Yes. And you'll often find that it does quite a lot better than this modern computing machinery that calls itself the optimizer. So, yeah.
So with that, we'll dive right in, and we'll begin with a discussion on estimation.
Yes.
Or how the query optimizer tries to figure out the right thing to do.
Yeah. So in order to do its work, it of course has to use histograms. This shouldn't be a surprise to you if you're in the room. And we have all these different types of distributions. We generally don't have a problem with the keys because we know that the keys will always deliver exactly one when we search on them. So that's the easy problem. We have these natural distributions that are sort of nicely placed, like the one in the middle there. But as we shall see today, both in the case of the nice ones, but also especially in the case of the skewed distribution, you get into all sorts of interesting problems with the optimizer, even when you have updated your statistics with a full scan. Even when everything else is correct, all your indexes are in place, your data model is exactly what it should be, and your statistics are fully up to date, you are still going to get in trouble. So all the usual best practices that you would apply simply just don't solve the problem for you. This is particularly true when you do reporting systems. Yeah. One of the first perks of the optimizer is that there's a lot of hard-coded things in there. One of them is that if you estimate something to be 0 in the optimizer, which is actually not that uncommon, certain queries expect to return 0 results, or maybe there's just something that isn't in the histogram for one reason or another. The optimizer will generally round that up to 1 and just assume that the value should not be 0, because certainly no one would ask for a 0 value. So it just picks the value 1 instead. That has some very interesting side effects. You could assume that that might actually be a good thing to do, assume it's 0, but there are very valid queries where you don't want that. So for example, we have an interesting little demo here. Adam is going to be my demo controller, because he has mastered the art of Dvorak keyboards. So I'm basically unable to operate his laptop. Okay. Here's a very simple example. This is something that a person walked up to me on my last conference and presented to me. We have, as you can see, 3 different tables, a small one, a very tiny one, and a little bit larger table, and we have populated them with some values. We can see here. This is just taken verbatim from the example that was provided. And notice now, as we run a query like this on the table, we have a very narrow row here. So should we look at? Oops. Oh, well, we probably have to be in the right database.
Yeah, let's do this. So here's
this looks like a very long running query. Notice how the we are filtering on the foreign key, and it actually returns 0 rows. The estimate coming out of the you see the filter we have here on the foreign key, foreign ID equals to 3 on the tiny table here, is assumed to be 1 instead of 0. It rounds it up. And because it does so, all of the rest of the plan behaves exactly as if it had done a key join. And what we then end up spending our time waiting for is, of course, this rather expensive sort and the scan of the 2 tables that lead into the nested loop coming over there to the left of the plan. So here we have an example of we actually wanted 0 rows back. We had to put a filter in there, and it just happens to be the result is a perfectly valid result. There's nothing in here. And because of this rounding problem, we're getting these really odd side effects of the plans. There's nothing you can do if you declare foreign keys, if you put full scan statistics, all of this will completely fail to solve this query. The only thing that you can do in this case is to force the optimizer to take the choice that you should be taking, which is, of course, to apply the filter to the tiny table first, thereby executing instantaneously. Now, there's several issues with the optimizer here. One is the rounding error. The second is its preference for sorting early, which is a bit of an odd choice in this case, since you don't really know that the filter returns anything. And it's failure to choose the filter table as the driving table. The only valuable filter on that table is actually the tiny filter, and yet it doesn't choose that as the driving table. So here's a good example of where we simply just have to force the query. Adam?
Back to it. I think it's still you.
Yes, we go to the slides and we will. The next one, I'm afraid we won't have the time to demo, but this is a very classic example. It happens all the time in data warehouses. And what you have here is a very simple join between a big table and its dimension. And we're doing a simple aggregate. This is the classic data warehouse query pattern. And what you have is this, exactly what we would expect to see from this. A clustered index seek. There's a nice little filter there. We go in there, repartition the stream, we get the bitmap filter, very valuable way to make this scan here a lot faster. And we get the expected parallel plan. And the reason that we get that is, of course, that we're hitting the histogram over there at the very side of the histogram. Now, imagine now that we take the same data and we add it into the table one more time, but advance the date 1. This happens all the time. You run your daily night ETL, and you will now have the same data one more time, or approximately the same data. If you're working on a very large table, because statistics update is not a multi-threaded operation, what you now end up with is a situation where you will not have valid statistics on the table, even if you have enabled autostats. And for those of you who would have wanted to run a full scan on the table, you'd quickly discover that that would be unfeasible. You wouldn't be able to run a full scan as fast as you can insert the rows, because it's single-threaded. And typically the plan you end up with is this one. Notice there's a few bad things about the nature of this plan. First of all, it's single-threaded. And secondly, it decides to run a sort very late in the plan. It doesn't actually make use of the bitmap. It doesn't even do a hash join. This is the worst possible plan you can get. And it will happen every time that you do this. Because what happens is that the histogram doesn't contain the rows that we're searching for, even though they are actually there. The opposite of what we just saw. Now, how do we cure something like this? What can we actually do about this problem? So there's a few treatments that are known to this. One of them is the trace flag, which is sparsely documented at best. And if you enable this trace flag, what will happen is that the SQL Server optimizer will know that if you're not hitting something that is inside the histogram, so if you're hitting outside the boundary of the histogram, it will try to approximate what it should be. And thereby it will make the original assumption that the day that has a lot of data in it is the one that's representative of the query. And this all seems very well and good. Unfortunately, in the table where you need this the most, the large ones, the ones that are partitioned, this no longer works. This is only enabled for non-partitioned tables. So far, I have not found a fix for this problem, except to do something that is unsupported, which you can visit my blog to see how I do, namely to create fake statistics on the table, something that you shouldn't be doing, and yet when you do it, it wonderfully solves the problem that you have. All right. I'll let Mr. Mechanic do the demo here of the many.
No, first it's the correlations.
I think we would show the many one first.
Okay, fine. So we were going to talk a little bit about further misestimates. We've already seen some, but we've not seen the worst of it yet. Maybe we have.
I'm sure.
You'll have to judge which is worse and which is maybe slightly better, or maybe they're all really, really bad. But let's just go out and run a simple query. And I'm going to go into my AdventureWorks database, and I'm going to run this simple query here. And what it does is it takes this table called Big Product, and it joins it to this other table called Big Transaction History. These are some blown up versions of the AdventureWorks tables. Very simple query. Has a little join, filtering on a couple product IDs, calculate a couple of row numbers, and then we'll just take max from all of them so we don't have to send a bunch of rows back to the screen. And I'm going to go ahead and run that. Query. Include actual execution plan, go. And we have a little coffee break.
Quite some time. The max trick, by the way, is a very easy way to make sure that you don't have to measure the time it takes to return the results to the client. There are other ways to achieve the same effect, but this is one way to do it. We'll show you another.
Let's look at our query plan. Nice parallel query plan, we like that. seek on big product, seek on big transaction history, a little hash match in there. And what's this? Let's see. Now this is a parallelism icon, and this one's also yellow, which is rather funny because it makes it difficult to see. But you'll notice there's a different icon, and that icon says that that sort did not have enough memory, and it spilled to disk as a result. And the way that it determines how much memory to use is based on estimates. The optimizer makes that choice, not the query processor. The optimizer knows only as much as it can estimate. It doesn't know reality, it knows estimates. So let's see how big a mistake it made. Well, it wasn't a huge mistake. It estimated 2.6 million rows. In actuality, there were 3.1 million rows, but it was enough of a mistake that we spilled as a result. So we need to fix this somehow. And we could update statistics on this table all day long, and it won't fix the problem. Because the optimizer deals in terms of averages, and we have a little bit of skew in our data in the table. So what are we going to do? We could buy a faster TempDB hard disk. Maybe. We could put in more memory. It won't help at all. We have to use our brain and take control. So here's what we've done. Created a function here, and the function is called mini. And what it does is puts all these rows in. Few rows.
Rather tedious to write in the first place.
Took me a long time to type that. And then it cross-joins all those rows together, and it returns values where row value modulus of 2 is 0. Now, what is 1 modulus 2? 1. So this will never be 0. My brain knows this. The optimizer does not know this. So now, when I run it, let me go into my database here. And we ask for a certain estimate. Let's do query, include actual execution plan. And I'll ask for 100. Oops. That's not good. I don't want help. It returns no rows, but the optimizer thinks, we have to go here, that it was going to return 100 rows. And by using that, we can influence the estimate as much as we want. So if I come back to this query, and instead of just running the query as is, I outer join to my dbo.mini function as though dbo.mini were returning 2 rows. What does that do? It doubles my estimate without increasing the actual row count or changing the results 1 bit, because there is no actual row. And when I run it, instead of taking, what did it take before? 16 seconds. It instead takes 4 seconds. And we come over here. There's no spill. And my estimate, much better. I went a little bit higher than I had to, but that's OK. I'd rather go higher and have good performance than have it lower and bad performance, personally. That's just me.
Memory is a cheap resource.
So should we jump back to the slides for a moment?
Yeah, let's have a look at the
Just close
some of the other examples. Now, when you find yourself, what we've seen so far is misestimates of simple join cardinalities, and misestimates where 1 gets rounded off to 0 and the other way around. Unfortunately, there are other types of misestimates where the filters by the optimizer really don't do the right thing anymore. The good example here is that I live in England, I eat a lot of scones. I pay in currencies pounds. You know, the one that has a high value nowadays. I live in London, I shop in English stores, and because the English are actually one of the few nations on the planet that eat scones, chances are that if I am buying a scone in a store, there's a high correlation between the fact that I am buying this product in England, paying with pounds, and buying it from an English provider. So if we look at, if you imagine that we had tracked all of the trade that happened in the world, and we have a store that sells bakery goods, for example, We have a good example of that in our data here. Let me just illustrate the table we have. We have a fact table. We call it fact world trade.
Well, that's down here. We have a bunch of dimensions first.
Sorry?
We have a bunch of dimensions first.
Yes, a lot of dimensions, the products.
So here's our scone.
So here's our scone product. It also has different names in other languages. We care not about those. We have the British Empire. We are coming from the region code, Great Britain. And you can see what we're introducing here is our world trade. And we have made sure that there's a high amount of people who buy scones, because there are many Brits in the world, even in other countries. And we only look at, of course, the people who are civilized. And who live in London. So this creates us a world trade fact table with a lot of people who buy scones and a lot of other products that they eat in other countries. Who knows? So if we ask the database for a list of all people who eat scones and when they were born, to see how the consumption of bakery breakdown by age group, we'll run a query very similar to this. And if we have a short look at that, there's something quite interesting showing up in our execution plan. You might notice that this takes a very long time to run. This is not a particularly large table. And here's our results. And observe there's some very curious behaviors here. One of them is that if we look at the very right here, we see another high misestimate. If you go to the left, please, Adam.
Oh.
The sort here is again misestimated. Quite
Let's
significant.
check out what the estimation
Let's
is.
see how bad that actually is.
So
That's quite significant, isn't it?
2.0 versus.
And as we track, here we have a nested loop join. This is quite unusual. All the other tables, except for the World Trade table, are small tables. And yet we get a nested loop join into one of our dimension tables here. 2 of them, in fact. This is a very inefficient way to join a dimension with a fact table. And if we track the plan all the way to the table scan, then notice the estimate coming out of the table scan here. The estimation, the actual, is already wrong at this point. Notice the bitmap provides us with a misestimate here. This bitmap gets pushed into the table scan. As it comes out of the first hash match, notice how the misestimate now again becomes even worse. And as we proceed through the query plan, we progressively get a worse and worse estimate. Because the query optimizer assumes that every filter is equally valid and that there's no correlation between those filters, which is of course not the case when you eat scones. So here we have an example of the filtering multiplying each other. There's one way to get around this is to try to create correlated statistics. Unfortunately, that means that you will need to create correlated statistics on every single combination of columns that you might query. A long task by any stretch. The other way is to force the query plan. And we can see an example here of where we're forcing the hash to happen in the right order, forcing a hash group at the end instead of a sort, because we know the result to be small. And here we are, about 10 times faster. Simply because the optimizer makes the wrong assumptions about how filters apply to tables. It does not understand correlations in the data. This, by the way, is multiplied many times with column stores. Makes it a much worse problem when you start using column stores.
Important to mention, we still didn't fix the estimate. We just overrode the bad decision being made as a result of the estimate.
And we'll see that there are actually ways to use our many function instead, even though we are exponentially off in our estimate here.
Should we go there?
Yeah, let's do that. So here we use the wonderful many trick.
So our mini function, so our estimate was, what, 300-something thousand times off?
Yes.
Something like that?
About so.
And unfortunately, the mini function, the way it's written right now, has been optimized to be as small an impact on the overall query plan reading experience as possible. So it only can estimate up to 185,365 rows. But that doesn't mean I can't use it twice, or 3 times, or 4 times. I don't really need it more than twice. If you have to estimate up that many, that's a lot. So right now we're doing 185,000 times 185,000. which I can't do that math in my head. And this is the same query that we saw before. We're just joining choice. And let's run it. Now the other query took about 4 seconds with the nice hash join. This one took a tiny bit longer. Well, it had to produce that execution plan. Let's just try once more.
Still much faster than the original estimate.
About 5 seconds for the full query, so a little bit slower than forcing the plan. Much faster than the original estimate. And the reason it worked, if we look over here, our mini function was included once. This is the mini function. No rows came out, but we had a nice big estimate, only 10,000 there. And no rows again, but again, a nice big estimate of 185,000. So our total estimate coming into all of our work that was spilling over here was a mere that. So no big deal. So what we've told the optimizer is, we don't care about memory limitations. Give us all the memory you can. We want to fly. Right?
Yes, absolutely. And you might have noticed that there was a trace flag used in the very bottom. We should come back to that later and how exactly that works. I think we should have a look at the slides again.
Should we see if there's
any questions at this point? Not the
Early?
case. Really? Everyone is following us so far? Very good.
There is no way to just tell them to give you more memory?
No.
There's no way to tell it to give you more memory, is the question.
Yes.
And the answer
You
is
can-
no.
you
We are
can-
telling it. This is the way.
There's a way for you to configure using Resource Governor, the execution engine, to be able to acquire more than 25% of the total memory allocated to SQL Server, which is the current limit for each query. So you can do that, but that doesn't change your estimate.
There's a way to tell it to give you less, actually, which is Resource Governor.
Yes.
But it won't give you more without using this. So, all right.
Very well.
So next we're going to move beyond estimates, and we're going to talk about the glories of parallelism.
Yes. With parallelism comes some unique challenges, because especially when we run in data warehouses, what we aim to achieve is, of course, that as we add more computing resources to our system, we will also run faster and thereby have a good return on our investment in hardware. That's one thing. We don't want to drop off the cliff and create these very poor scale curves. As you see, a lot of those are built into the product, the poor ones, that is. And another desirable outcome of parallelism is that, as Adam has shown here, that the CPUs go to 100%, are fully utilized. After all, that is the resource that we license. And at the end of the execution, they all drop off at the same time. There's no jagged sawtooth type pattern to the CPUs. So that is what we want to achieve when we configure SQL Server for parallelism. And the way that SQL Server makes that choice is by this rather complicated formula. I hope you follow it so far.
Shall I go ahead and go
Please
through
do.
this? So
Enlighten
before we
us.
can even get a parallel plan to run and hopefully be optimal, we need the optimizer to be willing to give us a parallel plan. So here's how it works. First phase of optimization, the optimizer comes up with a serial cost for the plan. And the serial cost actually has two components, a storage cost and a processing cost, or a CPU cost. After that, the optimizer says, does this serial cost exceed a setting that you might have seen in SP configure called cost threshold for parallelism? If it does, then the optimizer, in a later optimization phase, will calculate a parallel cost. And the parallel cost, it takes the CPU part only of that serial cost, divides it by your number of processors or number of schedulers, as we say in the SQL Server world. Then it adds back the storage cost, and it adds an additional cost for the parallelism iterators that appear in the parallel plans, which are called exchanges. Finally, if the parallel cost is less than that original serial cost, then you get a parallel plan. It's rather simple. All right?
Absolutely.
Unfortunately, various things that we can do will completely inhibit the parallel plan from happening. Serial plan will be necessitated if we have a scalar T-SQL UDF. You might have heard that scalar T-SQL UDFs aren't the best thing in the world. This is one of the reasons. Modification of table variables, bad thing. And the worst thing, improper costing. This costing algorithm that I just went through quite often results in a very, very big, very expensive plan running serially. Likewise, there's some things that cause serial regions in your plan. The biggest issues being data skew and the exchange operator itself, which is implemented in such a way that if data comes in the wrong way, the exchange iterator becomes, in effect, a serial zone for the whole plan. That doesn't make a lot of sense to me.
No, that does seem like a very odd choice.
So
But we shall see exactly when it happens.
shall we take a look?
Let's have a look at that.
All right, so we're going to go back into our database here. And why don't you...
Yes.
Yeah,
So we have created some tables here, simulating a fact and dimension table. These are just tables that have we have on purpose introduced skew into the fact table on the dimension key. So we now have a fact table where the vast majority of the keys are in one dimension. We have this very skewed distribution, but there's still a lot of other keys in there. So if we scroll down to the query that we'd like the answer to, this one, for example, we want to look at. We would like to see when it is rainy in England. This particular query, and we execute it.
There it goes.
If we look at the execution plan of this query, something very peculiar happens. If we go back to the parallelism, first we go through the clustered index as we would expect with a bitmap, and notice the data coming out on the first one here, from the directly out of the clustered index scan here, please.
Oh, this one?
The cluster index scan on the fact table.
On the fact table. Should we look at the distribution?
Yes, let's have a look at the distribution of that one.
Okay. So F4,
Yes.
expand actual number of rows.
Yes. Notice that there's a reasonable distribution among the threads here. There's 8 of those executing in parallel. Not a particularly nice distribution already at this point, which is strange considering that we actually don't care about the order they come out on. Why is this not equally distributed? But it gets worse as we go through the exchange operator. So here we have the repetition stream operator, and look what happens when we come out on the other side of the repetition stream. Look at the skew that happens there for thread number 3. For all practical purposes, this operator, which is meant to introduce parallelism, actually introduces a single-threaded bottleneck. And the reason it does so is that if we look at how it hashes here, you can see that the way it partitions the columns is that it uses D1 as the partitioning key, which we know to be skewed. The optimizer knows it to be skewed, the statistics knows it to be skewed, and yet the repartition operator still decides that it would like to partition on that one. And the reason it decides that is, of course, that that's what it's going to be hash matching on in the next step of the plan. This is not a plan that favors large machines. This is a plan that favors small machines. We can do a little about it. There's an example here we have of how we could rewrite this plan. Oops. This is not a good solution, but it illustrates the principle. Notice that what we have done here is that we have introduced a new column, foo, that we know to be less skewed than D1. And we're now going to group by foo, again picking a value the optimizer cannot second guess, 128 modulo foo, and nest that, and then surround that with another query that actually groups by the day of year, which is the original question that we asked. Now, if we execute this one instead, and we look at the execution plan, first of all, notice how much faster that was. And we look at the repartition stream here. Now, foo, unfortunately, has not been designed to be fully distributed. Unfortunately, the column foo, because of the way we have created the table in a hurry, I might add, was not completely distributed, but it is much better than before. But notice there's still a problem with thread 4 here. We could have designed foo in a better way. admittedly, which would have given us even better execution.
That would have been the foo bar.
That would have been a foo bar, yes. And if we look at the parallelism operator, we see now that the partitioning happens now both on D1 and foo. So we can introduce a fake column. For example, if you are doing this for the fact table, you could do this on a measure instead of a dimension, or a dimension that you know to be nicely distributed. And if you have neither of those, you could simply introduce a column that is always in the fact, and thereby creating a much more equal distribution of this. This is not a desirable solution, but it does help a little bit on the problem. You saw that there was about a 2x speed up here.
Oh, were we going to go back and do that other thing?
Oh, yes, please illustrate this trace flag and how that works.
Okay.
Remember the trace flag that we saw in the query before? The one that overestimated to 2 million rows?
It wasn't here, sorry. Was it? Which one was it in? Oh, correlation.
Correlation, yeah.
There we go.
There we have it.
Okay. So you might have noticed in this query that we have this thing here called query trace on 8649. That's a little odd, isn't it? Let's take it out. Now this query took, well, let's remind ourselves, shall we? Let's run it again. It runs in about 3 seconds. And now let's take out query trace on 8649. Let's run it again. And now it's a little slower, isn't it? So this trace flag is magic, apparently, because it's automatically given us a faster plan. A significantly faster plan. That took 15 seconds. So what just happened there? Well, let's do this. Query include, actually, let's just look at the estimated plan here. This is without the trace flag, 8649. Notice this is a serial plan. And let's look at the subtree cost here. Now, the default cost threshold for parallelism in SQL Server, and this machine uses the default, is 5. A plan of over 5 is considered to be big enough to go parallel. This plan is slightly greater than 5, isn't it? So what's the deal here? Well, let's go ahead and look at the trace flag again. We'll run the estimated query plan. And the other one was 99 something. So now we get our parallel plan, and the estimation changes, and the cost has gone up. Now, cost is supposed to be an estimate in seconds of how long the plan is supposed to take on a certain machine, circa, what, 96, 97 in
About
Redmond.
the same as about as old as the difference engine.
How does all this the difference engine? So apparently that machine has really slow exchange operators, because basically the way that algorithm works that I showed you before, the parallel decision algorithm, it takes all of the CPU costs, divide them by the number of CPUs, and then it adds in all of this extra cost for the exchange operators. And it assumes that those parallel exchange operators are really, really slow. It assumes that they're badly implemented by the SQL Server team. And they actually are in a lot of cases, but they're not that bad. So what we've done here is, in trying to figure out if the parallel plan is faster, the optimizer has outdone itself and decided that the parallel plan must, in fact, be slower. But we've already seen, by using our brains, that that's complete.
Utter nonsense.
Insert whatever you like. And the solution to this is this trace flag, query trace on 8649. What it does, actually we have a slide on it. What it does is it tells the optimizer, no matter whether or not that estimated parallel cost exceeds the serial cost, if a parallel plan is possible, give me a parallel plan. It ignores that entire phase of the optimization process. Now, unfortunately, enabling that plan with query trace on requires a certain privilege on your server that you might not want to give to all of your users, that being sysadmin. So what I did was I used, again, my brain. I wrote a blog post, which you can find on sqlblog.com, and I introduced a function called make parallel. Make parallel plays a few light and playful games with the query optimizer. Makes it think that our query is about 1,000,000 times more expensive than it is, all processor time. Therefore, when it does the division, it's very much in our favor, and there's no way that the exchange iterators can exceed it. So that's the alternate solution if you don't want to give all of your users sysadmin. All right.
Has this been used by anyone here? Any users of make parallel? No.
Not yet.
Anyone who has wanted a min-up hint? No. No one has this problem at all, apparently.
All right. Anyway, let's talk about CX packets.
Yes. So the common perception in the SQL Server world is that CX package is an indicator that your parallelism is too high or wrong in some way or another. Here's an example of a simple insert statement that inserts based on a select. And indeed, we see that there's a problem here. As we increase the parallelism, our throughput goes up until we hit around 50 megabytes per second. And as we then further increase the parallelism of this statement, our throughput drops off until it almost approaches a single-threaded plan. Does this then mean that our parallelism is too high? If we look at the throughput here, and as we see that the throughput drops here, we look at the last part of the graph as we start and move towards the slower throughput, the CX packet weights do indeed increase exponentially. Yet, at the optimal throughput, CX packet still figures in the plan. It's still the major weight type of the plan is still CX packet. So CX packet is not an indicator per se of an issue with the parallelism. The fact that it goes up as the throughput goes down is a side effect of the way that this particular query is written. So very often when you see the CX packet, you would like to understand where in the query plan the problem is. You know that it's somewhere in the query plan, there's something waiting for CX packets. And there's actually a way to do this.
So CX packet is, in fact, I think it's important to actually define CX packet, which is, in fact, C stands for class, X stands for exchange, and packet stands for packet. These parallelism iterators that you see inside of a query plan are called exchanges. The job of an exchange is for one or more threads on one side of the exchange to push rows across to one or more threads on the other side of the exchange. And instead of pushing it row by row, it pushes in packets of rows. So there are exchange packets. There's a class in the SQL Server source code called C exchange packet, class that implements exchange packet. And CX packet is the weight type associated with that class. That's what CX packet means. So what it means, and all it means, is that there is a thread waiting on another thread to give it some rows. That's it. Now, interestingly, if we look in our waiting tasks DMV, and we have CX packet waits, which we will always have in every single possible parallel plan that you can possibly run, always, there's some hidden information. You go over to the right after you run your select, and there's this column called resource description, and there's all these weird numbers in there that you are going to ignore. And you're going to scroll further right, and there is a little thing at the end. It says node ID equals X. If you go into an actual query plan, and you hover over any of the iterators, there will in fact be a node ID shown on the tooltip, just like up there. And that node ID for the exchange iterators will correspond to the node ID that CX packet weight is for. Therefore, you can actually figure out which threads are waiting on which nodes in your plan. Or to phrase it another way, you can figure out where in your plan the threads are waiting, thereby enabling you to figure out why you have such high CX packet and whether you can speed up the downstream sections. In other words, get those rows to those threads faster so that they don't have to wait as long. Your goal with CX packet is never to fix the CX packet, it's to fix the stuff feeding the CX packet. That is how you debug these things.
Of course,
A bit
one needs
more
to
on
use
that.
the brain quite a bit to come up with fixes. Because if they were easy, the optimizer would have done them.
Next.
Yes. If you are curious about where the CX packets are coming from, not just from a perspective of where in the operators, but you want to understand where exactly inside the operators it's coming from and gain a deeper understanding of CX packet, it is often a good idea to look out for other weight types that correlate with CX packet. So in the case of this, this was an insert statement that we saw before, the correlating here. Could be latch EX, or for table scans in 2008 R2, you will often find this. Apparently this has been solved in 2012. We couldn't reproduce it, we tried. We will see that there's a CX packet weight, but there's also a latch EX packet weight that correlates with the CX packet. As CX packet goes up, so does this weight. And it's possible to dig into latch EX weights using the latch stats, and what you find here is, is this weight, which is cryptically described in books online. This is the documentation. This helps us very little, but we have found that this is the access method we're waiting for. But there is a way for us to tease this information out of SQL Server without needing to read the source code. And what you do is you use a tool called XPerf, which is freely downloadable from Microsoft. There's a graphical user interface now called PerfView, which gives you the same information. And what this allows you to do, using, for example, a trace like this, is it allows you to zoom in on the query. In this case, we see the query executing here, the high CPU load. And by zooming into this CPU load and asking for the breakdown of this into its call stacks, one can see something like this. There's a call stack, and this call stack can be decoded for even by people that are not inside SQL Server, simply by setting up the tool correctly. And what we can see here in this particular case is that this CX packet comes from a heap set data session, get next row values, set up next subscan, and then finally we have latch base acquire internal, which is the one that correlates with our latch EX. And we can then make an educated guess that this is something that happens inside the table scan operator, and that we need to somehow speed up the table scan operator. In 2008, the trick here is to partition the table, and that will actually give you more table scan operators operating at the same time, greatly increasing the scan speed that you can achieve. So for those of you curious about exactly where the CX packet weight is, this tool is a very good way to essentially reverse engineer the engine. Okay.
We want to skip that one.
Yes.
All right, we already showed that.
Yes, we've seen the skewed scan. Hash join is the bread and butter of the reporting system. You will see hash joins in column stores. You will see it in almost all facts joins to dimensions. And at least in theory, what you should see is that you should see a hash join that is proportional to the rows that you, from the large table, typically the fact, you need to touch all of the rows there that you want to hash join with, and the rows in the smaller table, typically the dimension table that you're building a hash table over. This works very well when the hash function is good and there's good distribution. Then you get very beautiful join complexity, and this is indeed the fastest way to join. However, to do a hash join without a column store, you need to see the exchange operator that we saw before, the one that does the skewed distribution. That is one of the problems you can have. But even if the distribution is not skewed, even if the hash is perfect, and you get exactly the distribution you want, the mere act of redistributing the rows in itself is not scalable. And here's what it looks like. As you increase the parallelism of something that hash joins, we would expect to see a linear increase in the speed of the query, the upper of these lines. In this very simple scenario here, where we're just joining three tables together from TPCH. But yet what actually happens is that the hash join very quickly stops delivering additional throughput, around a degree of parallelism of 16. And after that, the redistribution itself becomes the problem. So if you find yourself on a large machine that has more than 16 cores, and you see something that looks like this inside your data warehouse query plan, where you have a table scan at the very bottom and my dimensions coming in from the top, and the redistribute operator here operating on the table that comes out of here, expect, and it's quite curious that the exchange operator does look like skull and crossbones, because that is what will happen to you as you start increasing your degree of parallelism. So how do we work around this problem? How do we avoid encountering the scale bottleneck of the hash join?
Well, what we can leverage is, instead of the hash join, the loop join. Now, it's interesting, the loop join complexity. We go log n.
Did you get that the wrong way around?
Log n.
Sorry?
That should have been m n. Oh, that's the m times log n rather than m plus log n.
Yes.
So if we compare the complexity of m times log n, so m being the outer rows, looping into the inner table, and each inner seek costing log of n. If you multiply, m times log of n seems often greater than n plus n, yet that's pure algorithmic complexity, and we can lose a lot of the stuff along the way. We can throw out some of the query processor's garbage. So let's take a look at it in a demo instead. So here's
What you're about to see is a trick that works very well indeed, but where you would have to ask yourself why you have to do this in the first place.
So what I'm going to do is run a query, and it's going to look like this. It's going to join these tables that we saw earlier. Big product, it's a big transaction history. We're going to join on the product ID. We're going to filter on the product ID. And we are going to calculate a couple of ranks along the way. These are windowing functions. We're going to partition by product ID. And what I'm going to do is, before I run this, I'm going to go to query, and I'm going to go to query options. I'm going to go to results, then to grid, and discard results after execution. You should know about this checkbox if you are tuning queries. And the reason you should know about this checkbox is that the grid in Management Studio is very, very slow to render your results. And quite often what you'll find if you're tuning a big query that's returning a lot of rows is that you'll spend a couple of hours playing around trying to get a better query plan, and you'll hit F5 and you will find that you haven't made a single bit of progress at all. But guess what? It's not you. It's Management Studio. Management Studio takes so long to render your results that it overshadows any gain you will have seen. And that's exactly what would happen with this query if I were to run it and actually show you the results. Now, the good news is, if your application is coded properly, it doesn't have this same scalability problem. So your application will see the benefit of your hard work. So I'm going to go ahead and check that. I'm going to hit OK. And what's going to happen is this is going to run. We're going to get an actual execution plan back. And we will see what the timing looks like, and we'll see what the query plan looks like. So that's running for a couple seconds or minutes or something. We'll see what it is.
Crunching away.
OK, there we go. It took about 9 seconds. And what we can see is that several things have happened here. First of all, we've done a seek out of the big product table. We've done a seek out of big transaction history. And then both of these seeks have been repartitioned. And the reason they've been repartitioned is so that this hash table can operate. So this hash match is on the product ID column. And so that each thread can build its own hash match and join like product IDs to like product IDs, both sides of this equation have been repartitioned using hash partitioning on the product ID column. So we've moved a bunch of rows. We've taken rows out of the tables, we've moved them across threads, and we've joined them together. And now the join comes out, goes into a sort, segment sequence project, that calculates the first rank. Then we need to sort again for the second rank, and oh look, our friend, the spill, back again. We've had a misestimate. Interestingly, not a very big misestimate, and still we had a spill. Is that fair? It should give us a little buffer or something, 10%, anything. Come on. Help me out here, SQL Server. But no, it doesn't. So this is not a good situation to be in. And so what we want to do is eliminate all of this garbage. We want to get rid of these repartitions. Well, this one might not matter, because that one's tiny. But this one's repartitioning. This one is moving 2.4 million rows on our behalf. That's not cool. We want to fix the estimation problem, and we want to maybe even decrease the size of the sorts so that mathematically we get better results. And how do we do all this? Well, we need to think about the query in a different way. We're going to move one of our joins. Now, if you go Google Amdahl's law, you can read about the computer science behind what made me think to try this in the very first place. And what you'll find is that Amdahl's law illustrates the relationship between a parallel plan, its serial version, and how well things will tend to behave given certain conditions. Should have put in a slide on that. Anyway, we're going to move the big product table. Instead of putting it in a join directly to big transaction history, we're going to move it out to the outer side of the query. So we're going to select from big product, and we're going to filter out here, so we get only the product IDs that we're interested in. And then, for each product ID, logically, we'll cross-apply, and we'll hit big transaction history just for that product ID, and calculate our ranks just for that product ID. And the result when I run this is a very different query plan. And the other one took 9 seconds. This one takes 6 seconds. I know you didn't see any results, but the counter stopped counting. So we've gotten a little increase in time. Modest, but hold on, we're not done yet. So we've gotten a, what have we done, 33%? It's not bad, right? I'll take it. As you can see, the query plan is very different. We start with big product. For each row in big product, we loop. We hit the big transaction history table just for that product. We sort just the rows for that product. Calculate our rank. Sort again. Calculate our rank. Notice that the sort, the second sort, does not spill this time because the optimizer is able to do a much better job of estimating the average number of rows that it will have to work with to do these sorts. And so it doesn't end up with a misestimation problem in this case. And then the rows come out into a single parallelism operator to gather them all together and come back to our caller. Now, we only went from 9 to 6, and we've been showing you much bigger gains than that. So you're probably saying, this is a little iffy, but let's use our brain once more and take a deeper look at the plan.
I think it's also worth noting that the exchange operator now disappears from inside here. So on a larger machine, this is a much more scalable solution.
All right. Well, hold that thought. Now, in our prior version of the plan, we were using all 8 cores on my machine. When I hit F4 here, actual number of rows, and expand it, we find out, wait a minute, we were only using 2 threads. So I got that 50% speed up just now and used 1/4 as many CPUs to process that query. But you know what I like to do? I like to use all my CPUs. So.
And why didn't we?
Let's do that.
Why didn't it just spread them out equally? Because that's what we would expect to see, wouldn't it?
Go and explain it.
Well, you see, the problem is that as we come out of this index seek up here, the rows, there's very few rows in product. And as they come out of the product table, we can only drive the nested loop by page. And there's very few pages in this table. Now, one ugly way to do this would be to make the product table very large by padding every single row so that each row is a page. This is not a very good solution for a lot of reasons.
It's better than you think, actually.
It's better. Sorry?
It's better than you think.
It's better. Yeah, it's not too bad. It doesn't work for very large dimensions, but then again, they have more pages. But because the dimension is small, we just cannot drive enough parallelism through here into the lower query. But there is a way to achieve that.
So interestingly, the query optimizer actually has a feature that was supposed to kick in here and fix it. If you want to Google it, it's called Few Outer Rows Optimization. Few Outer Rows Optimization was supposed to work here. It didn't, so we use our brain instead, once again. I replace my direct query against the product table with a query including a top iterator. Now here's the funny thing about parallel plans. Now what is that number? That's just the maximum integer value. I know for a fact that there are fewer rows in the big product table than maximum integer value. I know that that will always be the case. So therefore, this query is always 100% logically equivalent to the prior query. And I also know that in order to calculate a top, the query optimizer must introduce a serial zone in the plan, as we saw before on the slides. Furthermore, I know that if the query optimizer wants to continue processing in parallel after the rows have been in a serial zone, it must repartition those rows back into parallel streams.
At the row level.
At the row level, not the page level, thereby giving us a decent spread. So when I run this, instead of 6 seconds, oh, it's going to take like 20. No, it took 2 seconds. 2 seconds. We look at the plan. We see now we have a serial seek of the big product table. The serial seek feeds into our top. The top feeds into a distribute streams exchange operator, which uses the round robin partitioning type. That means that the first row goes to the first thread, the second row goes to the second thread, third row goes to the third thread, and so on until we run out of threads, and then we go back around to the start. So coming off of here, we get completely even, completely beautiful thread distribution. All the same stuff down here underneath the loop. No spills on our sorts, no exchange operators, just data coming out of our table, straight through, back to the caller. Beautiful stuff. Any questions?
How long did you study math? How long did you study math?
How long did I study math?
Yes, because it's
Since kindergarten, just like most people.
my brain couldn't complete it.
Ah,
It's very impressive.
thank you.
I noticed, though, that there is one assumption that drives this, which is that you have to have an index on the product in the fact table here.
Yes, that is one thing. You do want, if you see a key lookup here, you are doing yourself a large disservice. If you see an index scan here, your user's not going to get anything back, because now you're scanning this table, 2,000 times. That might be a little bit expensive. So put an index on the table, please, and or just call me. I'll do it for you. All right. Shall we conclude?
Yeah, let's wrap up.
All right.
Question.
Oh, yes.
Yeah, is there a good way to put max, a top of max into an everywhere?
Is it a good idea to put the top in everywhere?
Is there a reason not to do it?
I don't know if I'd do it everywhere. It doesn't seem like a good idea, but I don't know if I'd say it's a bad idea.
Well, it would force. There are places where you don't want the serial part of the plan,
Oh, that's true.
where you just want the parallel part. If you were to, for example, put the top into the outer part of the inner part of the query, that would be a bad thing. Would not give you exactly the parallelism that you're looking for. So no, you only want it when you want to force this distribution. If you don't want to pad the rows, that is. That's not.
All right. Well, I'll let you summarize for us.
So just to summarize the tricks you have learned today, the ascending keys, if you are not partitioning your table, can be solved by these two trace flags that can be enabled. If you find yourself having a partition table, first of all, file a bug to Microsoft, asking them to fix this problem. And secondly, if you absolutely must, and you want to take the gamble that you're now into unsupported territory, go look at my blog on how to make this work. We've seen that with the many function, you can control the estimates, determine exactly how many rows we want to be estimated. If we know better than the optimizer, which very often is the case that we do, simply because we designed the data model. Parallelism can be forced with the trace flag, requires system administrator. Adam's function, make parallel, solve the problem very nicely for you. And then finally, this beautiful cross-apply pattern to drive the parallelism. Any further questions?
Yeah, about ascending keys. I believe there are some changes in the optimizer for that in 2014.
For the ascending keys.
Whether they actually work out in practice or not, I don't know.
So
Rumor has it that it should be working in 2014.
rumor has it that 2014 will include a fix for the ascending keys. Is Erlen's comment, and my comment back would be, I care about shipping product that actually works.
But one point, SQL 2014 will be shipped.
Okay, so if you're willing to wait a little while, all your problems will go away. Don't worry. Don't mind the man behind the curtain.
You know, you have to test the facts.
Yes, we'll see.
Yes.
The SR rights for the parallelism, you could fix that by using a certificate login and encrypt the plan, or sign the plan, right?
I suppose you
Create the login, drop it in the database, create your store procedure and sign it. That way you can give the SR rights, but only for that plan. Change it,
yeah.
signing
So the comment here was that if you want to assign the SA rights in order to use the trace flag, you can use module signing to do that. That is true, although I'm not sure that will work on a user-defined function, a table-valued inline user-defined function or a view, because you have to put the query hint on the outer part of the plan. That's actually why I wrote the function, so that I could use it in views. And the query hint needs to go on the outer side, and the users are hitting the view directly. So it's not always possible to use a store procedure, but I do agree with you. In a lot of cases, module signing would be fine there.
It can also be used to get the plan that you want, and then afterward use the XML to actually force that plan for other users by plan overriding. That's another way to work around the problem.
All right. Well, I think
If
we're all
that's
set.
it,
Thank you so much.
thank you.
And you can come up.